So a linear system of equations. So we have done linear equations. That's one equation that reproduces one line. And now we're going to look at systems of equations. This is going to be multiple equations that produce multiple lines, all right? And so the first thing they discuss is what is a system of linear equations. It's made of two or more linear equations. Any ordered pair that makes all the equations true is a solution to the system of equations. It's a solution to the systems of equations. Just like you graphed a number line to give me the answer to a question, we are going to look at graphs in this first section to answer the questions. So this first thing, just ask, do we have an answer? Is this ordered pair a solution? So in order for it to be a solution, which is what they're asking for, then it has to work for both equations. So the way I check this is I'm going to take my first point. My first point that they gave me was 11, 2. And I am going to see if it makes both equations true. So x minus y equals 9. That is true. 11 minus 2 does equal 9. All right, and then I'm going to plug it into the next one. 2 times my x minus my y equals 9. This is a problem, right? 22, or it's plus. Did I write minus? This should be plus. 22 plus 2 does not equal 9. That is false. So we would say that this is not a solution. In order for it to be a solution to this system, it has to work for both of them. So 11, 2 is not a solution. Let's check the second one, 6, negative 3. So we have 6, negative 3. We're going to do exactly the same thing. 6 minus negative 3 equals 9. That is true because it's plus a positive, 6 plus 3. 2 times 6 plus negative 3 equals 9. Well, this is 12 plus a negative 3 or minus 3 equals 9. Yes, it works for both of them. So you would say that, yes, this is a solution. So 6, negative 3 is a solution to the system of equations. 11, 2 is not a solution, all right? In order for it to be a solution to a system, it has to work for every linear equation in the system. That's what we're looking at when we're looking at, is it a solution? All right, so it says one way to solve systems of equations is by graphing. This is the first method we're going to use when we're solving systems of equations. We're going to use graphing. All right. It says graph both equations on the same coordinate plane. Identify the solution, the coordinates of the point of intersection. Check the solution by substituting it in. So here's the thing. If I have two lines, the point where they intersect is going to be true for both lines. All right, and so this is why we can use graphing. The point where they intersect is actually a point that is on both of those lines, which means it's going to be true for both of those equations that form the line. And so if we can graph it and see where they intersect, then we can tell if those two have an answer and what the answer would be to make it true. All right, so the first thing we're going to do is graph these. These are in slope-intercept form, so that's how we're going to graph these. First one. Like we always do, we are going to start at my y-intercept. My y-intercept here is negative 2. So I'm going to start at negative 2. My slope here is negative 1. You can think of that as negative 1 over 1 or positive 1 over negative 1, right? It doesn't matter. It'll be on the same line. So I can go down 1 and right 1. Or I can go up 1 and left 1. You can see that those are both on the same line. anytime I have 2 points, I can graph. So once I have 2 points, I can use a straight edge, or, you know, I would recommend that, but piece of paper, whatever works, and you are going to graph. All right, so I've graphed the first one. Then I'm going to graph the second one. I start at my y-intercept. My y-intercept here is -4, so I'm going to start at -4. My slope here is +1, so I can go up 1, over 1, or down 1, left 1. Usually when I'm solving by graphing, I will walk up my slope until I cross that line, because that's going to tell me exactly where I'm going to cross. In this case, it actually crosses right there. You can see up 1, over 1 will cross right there. All right. So that's my second line. My solution is going to be where these two cross, right there. That point is my solution. So my solution here is still going to be an XY point. I'm going to list it out. The X value of that point is 1. The Y value of that point is -3. That is my solution based on this graph. So this would be my answer. I can check my answer. How do I check it? Well, I plug it in. The first one is y equals -x minus 2. Y, -3, equals -x minus 2. -3 equals -1 minus 2. That's true. The next one is y equals x minus 4. Y, -3, equals x minus 4. That's also true. So that is the correct solution here for this one. So when it's not in slope-intercept form, you can graph using your intercepts. That's one way to do it. Or you can put them in slope-intercept form. The one thing I would say, graphing with intercepts, I only graph with intercepts like this if I'm solving by graphing, if I'm going to have perfect intercepts, not fractions, all right? So like, for example, these intercepts, well, x is going to be -5, y is going to be +5. That's easy. But here, I'm not going to have something as pretty when I do my x-intercept. I'm going to have a fraction. So typically, I will put these in slope-intercept form. The only time I don't do that is when I do a word problem, all right? So I'll typically put these in slope-intercept form because it also helps you walk to the line. So for this first one, I would take that x minus y equals -5, and I would put it in slope-intercept form. So I would move my x over. I have -y equals -x plus 5, and then I would divide everything by -1. So my first line is going to be y equals x minus 5. All right. Actually, that's going to be +x. Yeah, that's right. I was like, what am I missing here? Helps to put your minus right there. Let's put that there. That's going to be a plus. There we go. Much better. All right. So that's my first equation. I'm just putting that in slope-intercept form. And then I'm going to do the same thing with the second equation. I'm going to say 3x plus y equals -7. For this one, all I have to do is move that over. Y equals -3x minus 7. All right. And then I'm going to graph this. So I'm going to go to +5 on my y-axis. Always start on your y, +5. And my slope is +1. So I can go up 1, over, or down 1, and left. Either way, that's going to be where that one is. All right. Straight edge again usually helps you get it more precise. So that's my first line. My second line, I'm going to start at -7. Now in this case, here's the thing. This is what I meant by walking. My slope is -3 over 1. I can go down 3 and right, or I can go up 3 and left. All right, so here's what I would do. I'm going to say, okay, I start here, go up 3, 1, 2, 3, and left. All right, so that's a point right there. Up 3, left 1. All right. If I'm trying to get this exact to figure out what those points are, I'm probably going to do this 1, 2, 3, and 1, 1, 2, 3, and 1, right? So typically I will walk that slope all the way up. so that there's some room for error. If I were to just draw that line, if I just shift it a little, it's going to change where it is on that point. And I might be in between 2 points. Does that make sense? And so very often I will just keep walking. I'm going to keep walking up 1, 2, 3, and over, put a point there, and then 1, 2, 3, and over, and I can see this is where I'm going to cross that line. So I just kept walking using my slope all the way up, because if I were just to connect these 2 points, granted I would have graphed that line, but you can see I could have turned it this way, I'll be a little bit off, or what if I turned it another way and I would be a little bit off. So if I were to just draw it using those 2 points down there, I could potentially be off when I draw it, right? And you can see that I'm connecting the points, but human error is going to let me be off a little bit. So I will walk it all the way to the line to see exactly where it intersects. And then I will know I have the exact point that I need to, oh, that's not pretty. See, human error there. The exact point that I need for those two. All right. And then once I know the point, once again, I'm going to use my XY value. My X value here is -3. My Y value here is +2. And so that would be the solution to this one, -3, +2. And I can plug it back in to see if it works. -3 minus 2 equals -5. Yes. -3 times 3, so -9 plus 2 equals -7. Yes, it works for both of those. I know that's the correct answer. So I know that this is my solution to my system of equations. Solve the systems by graphing. So let's look at this first one. I'm going to put it in slope-intercept form and then graph. So my first one, I'm going to move my x over. I get y equals -x plus 3, right? So if I graph that, I get a +3 down 1 over 1, right? And I get this line right here. All right, so this is my first line. If I put the second line in slope-intercept form, all I need to do is divide everything by 2. Y equals -x plus 3. What's going to happen when I graph that? It's the same line, right? And so where do these cross? Well, they cross on the entire line, right? And so I don't have just one point that is my answer. I actually have an infinite number of points. Specifically for this one, my answer is the line itself. So for one like that, I would say my answer is y equals -x plus 3. Every single xy that is on that line works for both of those equations because they are the same equation, all right? And so that's one of your options. You can have an infinite number of solutions. If you have an infinite number of solutions, your answer is the line itself. It's not xy. It is the y equals mx plus b. The entire equation is your answer. Okay? So if they end up being the same exact line, your answer is infinite number of solutions, specifically the ones that are on this line. And so you're just going to box in the actual line equation, and that is your answer. So that's one special case, that you could have an infinite number of solutions. Let's look at the next one over here. All right, so I'm going to put it in slope-intercept form. All right. Or I could graph by intercepts. It doesn't matter. So for B, I get y equals negative x plus 3. So I'm going to start at 3, go down 1 over 1. All right, so that's my first one. All right. For my second one, in slope-intercept form, I get y equals negative x plus 7. So I'm going to start up here at 7 and go down 1 over 1. All right. What do you notice about those two lines? They're parallel, right? Could I have known that from this right here? Is there anything on those that tell me those are going to be parallel? What do I know about slopes of parallel lines? They have the same slope and different y-intercepts there, okay? These had the same slope, right? -1, but they had different intercept. I mean, they had the same intercept, which means it's the same exact line. Here we have the same exact slope, different y-intercepts, which means when I graph them, they're going to be parallel. Where do parallel lines cross? They don't. So for this one, I actually have no solution here. There is no point on the coordinate plane where those two graphs will cross, which means there is no xy value that will be true for both of those equations. You cannot find any x and y combination that will be true for both of those. It won't work. Whereas on the other one, any x and y value that works for this is going to work for that because they're the same line. These don't ever intersect. There will be no xy that works for both of them. So these are special cases. If you have the same slope and the same y-intercept, the entire line is your answer. If you have the same slope and different y-intercepts, those are going to be parallel. No solution is your answer. All right. So if you look at the bottom of page 280, here are the types of answers you can get. The first type is the most normal one that you're going to get. They just are two lines that intersect. When they just intersect, you have one solution, and it is an ordered pair, xy. That's what ordered pair means. So if you have just normal lines that intersect, you get one solution, ordered pair. Your other option, you can have parallel lines. Your answer is no solution. Your number of solutions is you don't have any, and your answer is empty set or no solution. So you can just draw that circle with the line through it. That means empty set, I don't have a solution. And then the last thing is they coincide. They are the same line. The number of solutions you have is infinite, and your answer is all points on the line. The way you give me the answer is you just write the line equation, y equals mx plus b, and that's your answer for that one. But two options for financing a used car. The loan from Bank A requires $3,000 down and $250 a month. The loan from Bank B has the same interest rate, but requires $2,000 down and $350 a month. Write a function to describe the financing options. So your amount down, you can think of that as your y-intercept. So you'll notice that the $2,000 down, that's a y-intercept. And then $350 a month, they were going up by $350 when they went over by 1 month. So y-intercept, slope, that's what they did. And then the other one was $3,000, and then it went up by $250 every single month. And so it's basically saying, where will we have spent the same amount of money? Well, after 10 months, you see he has spent the same amount of money for both loans. Here's the thing. And this section is solving by graphing. Solving by graphing is great when it's nice little like 1 through 10 and they are all the same units, right? But here I'm going up by 500 and I'm going over by 1. What are the chances I'm going to graph this incorrectly? Pretty good, right? I mean, the chances that I'm going to get the exact number that they fall on is difficult. And so there are situations where graphing is a really easy way to solve. And what we're going to do in the next couple sections is we're going to look at other ways to solve that are algebraic, and you're going to get the exact answer, even if it's a decimal. Let's say they were at 10.5 months is where it crossed. That's really going to be hard to do on a graph, right? But there are some algebraic ways for more difficult ones that say, hey, we can solve it algebraically. And so there are times when companies may want to just project, and they're like, okay, this is a trend. We're not trying to get exact, we're trying to get an estimate. Maybe they'll do it this way where they can just do a projection line. And then there are times when you want an exact, and we may solve it a different way than actually graphing, because you can see how human error probably would yield some problems here. All right.